Welcome to Lecture 11. Today we're going to move into lake effect snow forecasting, which to me is one of the most fun yet also the most challenging things there is to forecast. Obviously, forecasting is not easy no matter what you're forecasting, but I would argue lake effect snow forecasting is definitely near the very top of the most challenging things there is to forecast. You could have everything right, but be off by maybe 5 degrees of wind, and that could be the difference between feet of snow. So the gradients are incredible. I'm going to teach you a lot of tricks with this. I was blessed to learn this from Doug Gillum, who I've talked about before, who works for the Weather Network. He grew up in kind of that area there, and he taught me a lot of these tricks many, many years ago, and I've been using them for a long time now, and it works really well. I'm going to give you as much as I can, but being as honest as I can with you, this is tough. This is not easy. I mean, you're relying on the model data to help make your forecast, and if the model data is only off by 3, 4, 5 degrees of wind, that could be the difference of feet of snow. So it's really difficult. But at least I'm going to give you the background and the basics and the tools to at least give you a shot at this. At least you're going to have a much better outlook on it and at least have a good idea on it. And of course, like anything, it's just experience. The more you practice, the better you're going to get at this. All right, so we got our Great Lakes. We got Lake Superior over here, Lake Michigan, Lake Huron, Lake Erie, and Lake Ontario. All right. So this is the area that we most talk about lake effect snow, but lake effect snow doesn't just occur in the Great Lakes. You can get it in places in the West. You can, like I talked about in the last lecture, you can actually get ocean effect snow. So it's not just in the Great Lakes, but this is the more famous area, especially this area here east of Lake Ontario and the Tug Hill Plateau, also east of Erie. Not that these areas don't get a lot of lake effect snow as well, but these are some of the more famous areas that you talk about. Obviously, you have Buffalo here, which, it's about 1 million people. It's not a small city, all right? So this is what you're going to hear most about with lake effect snow. But keep in mind, it's not just in the Great Lakes. All right, so believe it or not, this is a streamer coming all the way from Lake Michigan, all right? So coming down from Lake Michigan that made it all the way to Huntsville, Alabama, the northern parts of Alabama. Obviously, there's a little bit of elevation influence here. This isn't some, amazing lake effect type streamer. It's just a piece was able to break off and continue towards Alabama and actually had a little fluke, little, if you want to call it, lake effect event. But it originated from Lake Michigan and moved its way down. I saw in D.C. some of these lake effect events where some of those will break off and move towards DC. Not overly common, but it does happen. While this is not overly common, it does happen. This is interesting. You're getting ocean effect rain and light snow here near Cape Canaveral, where NASA and the rocket launches are. You got an event where you had a similar type setup here in Jacksonville, Florida. A little bit of bits of snow mixed in, and obviously it's not accumulating, but anytime you get any type of snow in Florida, people are going to talk about it, all right? So ocean effect. This is one of the most famous and most common one is the northern parts of Japan get clobbered with ocean effect snow, I should say. So you get this cold air that comes from the continent over the relatively warmer Sea of Japan area, and obviously it's not like you'd go swimming in it, just like you wouldn't go swimming in the Great Lakes. But if the water temp's 40 or 35 and the air above you is -10, it's a heck of a lot warmer, right? So you can get ocean effect snow in Japan, and they get a lot of it. So keep that in mind. So this kind of goes back to the origination of it, which you're going to see in a lot of textbooks. It's a way oversimplification, but it kind of just gives you an idea of what's going on. You have a continental polar air mass that moves over the relatively warm Great Lakes. Now, obviously, the warmer this water is, and the colder the air above it is, the stronger the last race, the more instability you have, right? The more rising motion. But again, you're not going to go swim in the Great Lakes, but minus, or plus 1 or 2 degrees Celsius is a lot warmer than minus 18, 19, 20 degrees Celsius, right? So this cold air moves over the lakes. The lakes is relatively warm. You get instability, rising motion, clouds start to form. And as these clouds build and they start to, come on land and the friction of the land and also elevational processes and other things are going on, these all start to pile up and you start to get either snow or rain. We always talk about snow, but you get lake effect rain as well, all right? And sometimes these events are massive, and it's all about the duration, all right? you're getting 3 to 4 inches per hour. There's a big difference between a 6-hour event or a 24-hour event, and that's how you get the really big snows is the duration. So, oversimplification, but this is typically what you're going to see in a lot of textbooks or just journals or things you read. Here's a cool imagery. You got, like I said, Superior and Michigan and Huron, but you see how these are kind of look like stronger bands. You start getting dual lake interaction, all right? So you get multiple lakes working together, which will cause stronger bands, all right? So that's something to always look for. But just beautiful imagery here showing you the lake effect. Look at this, what direction are the winds? Northwesterly, right? You can see the bands streaming from more of a northwest to southeast direction. Kind of shows you exactly where the winds are, right? All right, so that's kind of cool. Here's something you'll hear people say a lot, that with lake effect, it will clear up stormy. And what does that mean? Well, in a synoptic scale event, what happens as the low ejects out and everything moves out and the cold front moves through, a lot of cold air aloft arrives, right? So the synoptic scale system goes through, you get your precipitation, it starts to clear up, but now all that cold air aloft is moving over the relatively warmer Great Lake water, and now you start getting lake effect snow. So that's the whole clear up stormy saying, right? The synoptic scale event moves through, you clear up, but then you immediately start to get stormy from lake effect, so you clear up stormy as that cold air aloft moves in over the warm, relatively warm water. All right, so here's some of the average seasonal snowfalls. And you'll see that the biggest snowfall is about 20 to 30 miles inland, where the frictional effects, and especially here in the Tug Hill Plateau, the elevation is influencing this, all right? And look at this, over 200 inches. I mean, that's some of the highest totals east of the Rockies, all right? So incredibly high snow totals. And Doug, he grew up here, of course, where it was, 50 inches of snow is still a lot of snow, but in this belt, that's not a lot. Now, 50 inches is way more than D.C. or New York, places like that get. But in the lake effect belt, it's not a whole lot. He always used to joke about that. But why are you getting way more snow here versus here? Well, where is the flow usually coming from? West to east, right? More westerlies, right? So in the mid-latitudes, you got more west to east flow. Yeah, sometimes you get north to south or east to west. It does happen. But these are the areas where the snow is really going to build up. And usually the heavy snow is about 20 to 30 miles inland. All right, so here's the ingredients for lake effect snow. All right, the first one, there needs to be a minimum of a 13-degree difference between the lake and 850 millibars. All right, so this is without synoptic. We're just talking about last race induced forcing, all right, without the synoptic scale enhancement. The synoptic scale will enhance these events, and we'll talk about that. But you got to have a 13-degree difference between the lake and 850. It's pretty amazing how this works. It's almost like someone turns on a switch. You start getting close to 13, and it starts to look like it's very fibrous. It starts to look like it's trying to form. Then you hit 13, and boom, they just start to form, all right? So 13 degrees Celsius is the minimum you need. Now, obviously, the higher you go, the more unstable it is. If you had an 18-degree difference or a 25-degree difference, the higher the difference, the better, all right? The more instability. And that ties into the lake index. When you read a lot of these discussions up in the Great Lakes, they will talk about the lake index in relation to this 13-degree difference. If they tell you the lake index is 0, that means there's a 13-degree difference. So when you reach that 13-degree difference, that's a lake index of 0. If you get to an 18-degree difference, that's a lake index of -5. If you got to a lake index of, or got to a difference of 23 degrees, that would give you a lake index of -10. So it's kind of similar to the LI, even though we know that LI in severe weather is very limited because you're just looking at 500 millibars and it's only telling you what's going on at 500 millibars. But if it helps you remember this, the more negative in general, the more unstable. So again, 13-degree difference, lake index is 0. 18-degree difference, lake index of -5. 23-degree difference, lake index of -10. So forth, continue, right? All right, you also need less than a 30-degree change in wind direction between the surface and 850 millibars. So unlike severe weather, this is more like tropics. You don't want wind shear. The less amount of wind shear, the better as far as lake effect bands are concerned, all right? And you got to think of it of almost like a hose, focusing the moisture, right? If you have almost no shear, it's like just running your hose, and all that water is one confined area. But if I'm getting closer to a 30-degree difference in shear, yeah, you still get lake effect banding, but it's not going to be as strong of a band. It's like if I put my finger over that hose, and then now the moisture is being spread out over an area. All right. So the closer to zero, the better as far as a more focused, strong band. And the hose analogy is a good way to think of that. If I'm getting close to 30, it's like me putting my thumb over it and I'm spreading that moisture out. Okay. So less than 30-degree change from the surface 850 millibars. You need deep layer of Arctic air, all right? And on Buff Kit, which this is what it was originally made for, right? It was developed can't remember exactly, it was right around, I'm going to show you an event in 95 where it was still kind of on the beta version, but right around the middle 90s, maybe a little bit before 93, 94, they're developing this program called Buff Kit, which we've used a lot for what? Precip type, and snow ratios, and you can use it for temperature forecasting and wind forecasting and all sorts of stuff. But it was developed, in the Buffalo area, Buff Kit, for lake effect snow. All right, so it has all these cool tools on it, and I'm going to show you some of that towards the end of this lecture here. But they use a lake-induced equilibrium level. I'm always a little cautious showing these numbers because it always depends on the situation, but about a 5,000 to 10,000 foot level. And when I say equilibrium level, what am I talking about? The top of the cloud, right? So the top of those clouds reaching 5,000 feet, you start getting advisory criteria. You start getting to 10,000 feet and above, you start leading to more warning criteria. Why? Well, the deeper the cloud in general, the more what's going to be available, the more moisture that'll be available. Plus, it's also showing you what? Stronger updrafts, and this is convective, all right? This is convective snow. I mean, we're going to look at CAPE and normalized CAPE and all different types of things with this, all right? So the deeper that cloud is, the more precipitation that's available, and typically the heavier the snowfall, right? All right, so keep that in mind. I'll show you a little bit of that on Buff Kit. Some other ingredients are really important. It was always assumed for the longest time that the lakes provide enough low-level moisture, but that's not always true. And that's something Doug really hit on with me. He said, you got to look at the profile. You got to look at that boundary layer and make sure it's saturated, okay? Because if it's not saturated in the boundary layer, you're not going to get lake effect snow. So you really need to make sure your boundary layer is at least 80, relative humidity, while not the best measure of moisture, is good for what? Saturation. So if you're saturated and you have all your ingredients, you're good to go. But you got to look at that low level. That's important. You got to look at the boundary layer. So you need relative humidity values 80% or greater. Obviously, the closer to 100, the better, but at least 80% or higher. You start getting lower than 80, especially 70, and it really will inhibit lake effect snow. All right, so make sure you understand that. Fetch is important as well. You need to be located downwind from an open lake, right? So if your lake ran west to east and you had westerly flow, then on the eastern side is where that band is going to come in, right? So it's not just the wind direction, it's the amount of fetch you have. The minimum typically, all right, is about 60 miles. You really need 60 miles or greater to produce lake effect snow. Now I'll talk about some examples where you can get a much lower fetch, but the longer the fetch, the better, right? If you have 60 miles versus 120 miles is going to produce a much stronger band. You have a much longer fetch. You're going to move that cold air over a much longer area of more unstable conditions, pulling in, causing that rising motion and instability and moisture to build up. And the longer the fetch in general, with everything else in place, the stronger the bands, right? Now, 60 miles is a pretty safe bet. Now, I've seen some weird things where you only have a few miles. Now, what would one way to, get past that? Well, when we're looking at winds, at 20, 30, 40 miles an hour, then you need more 60 miles. But if you only had 5-mile-an-hour winds, you may not need as much of a fetch. So the lower the wind speeds, the less the fetch you can get away with, all right? And it makes sense, right? I mean, if it's moving fast, then you have a short period of time that it's going to be over the water. If it's moving slower, then it's going to take its time moving across the water, all right? So the one way you can overcome that is slower synoptic scale winds, all right? And in general, these bands like to funnel along the lake. I'm going to show you in Lecture 12 a mesovortex example with this, but we'll get more into that later, all right? And the other thing to understand is, while this can be completely separate of the synoptic scale type event, and what I mean by that, the synoptic scale event is bringing the cold air a lot, but it's not like you have to have tons of, DPVA to get these things to go, and you don't have to have it at all. But when you do have a combination of some sort of shortwave mixed in with all these ingredients, and you do get some extra DPVA, that's sometimes when you get the difference between, a bad event or a significant historic storm, all right? And duration is the key, all right, between a major and minor lake effect event. It's really important to understand this, all right? So I'm going to show you soon, but QPF is worthless in lake effect snow. Again, worthless. You're talking so micro mesoscale that there's no way the model can see that, all right? I'm going to give you a case study where there was like about a 60-inch gradient in about 5 miles. I mean, that's crazy. No model can see that. Maybe 20 years down the road it'll get to that point, but we're not even close to that yet, all right? So the duration is the key. So how do you forecast the amounts, right? It's, okay, this is where the experience comes in. And I can't make you an expert in lake effect snow in one lecture. That's physically impossible. You're going to have to practice this, right? And if you are in an area in the Great Lakes, I'm sure you have been practicing this a lot. I would recommend having a notebook or journal and write this stuff down. Write down the ingredients and be like, all right, we had these ingredients and we got 2 to 3 inches per hour. Or we had these ingredients and we got 1 inch per hour, all right? Once you start getting those thresholds down and you go, okay, when I've seen these type of ingredients and we're getting 2 inches per hour and it's going to last 12 hours, well, that's how I get my forecast, all right? So if these ingredients equal 2 inches per hour times 12 hours, I'm going to go with 2 feet of snow, 24 inches, all right? That's how you forecast lake effect snow. Again, QPF is worthless. Don't waste your time on it, all right? Look at the profile, analyze the ingredients. Now, of course, you're looking at a model data, so you better hope that's right. And that's where the experience of coming in, which model's handling situations better, is really important. And look, the only way to do this is to put the effort into it. If you want to be good at this, it takes a long time and a lot of effort to do it, all right? There's no shortcuts on this. I'm giving you a lot of cool tips that are going to help you, but you still got to put the work in, all right? Experience is the key here. Know your area and history and practice a lot. A notebook, a journal, something like that would be really helpful. I know Doug used to do that a lot and it really helped him. And he literally got to the point where the way the synoptic scale, front would come through and the temperatures aloft, he got really good. I mean, no one's perfect, but he got really good to the point where he can just look at the pattern and know this usually leads to this, which again, the only way to do that is experience. All right, so some characteristics of lake effect snow. You can get snowfall rates up to 8 inches per hour. Of course, you can get heavy wet snow, but a lot of times, some of the highest ratios you'll ever see is in lake effect events. That 50-to-1 ratio, that's usually going to occur in a lake effect snow event, all right? Tons of omega, lots of rising motion, beautiful dendritic crystals, especially when you have no wind. Perfectly, stack up, and that's how you get your highest ratios. You can get, like I said, snowfall rates of 8 inches per hour, which in a nor'easter, if you're getting 1, 2, 3 inches per hour, that's significant. Thunder and lightning is very possible. This is convective, all right? We're dealing with not just CAPE, but normalized CAPE. And I'm going to show you a couple examples where you had really good fat CAPE, all right? Yeah, you didn't have a ton of CAPE, but the CAPE was located in the right area, and the lapse rates were through the roof, all right? I've seen some events where you had 12 or more hours straight of thunder snow. Pretty amazing stuff. 60 to 100 inch possible single day or multi-day type events. You can get well over 100 inches of snow in a week-long event. It's happened many times. Seen week-long events pushing 140 inches plus, if not even higher. One location may receive 40 inches in a day, while another location, 10 to 15 miles, may receive sunshine. Again, the gradients are incredible on this, and this is what makes it so difficult. I taught you these ingredients. You got everything down, but you're just off by 5 degrees on the wind. And think about that. If you were calling for southerly flow and you said 180 degrees and it was 185 degrees instead of 180 degrees, does anyone care? No, it's still southerly flow. But on this, everyone cares because it makes a massive difference. And what's interesting about these things, and Doug would tell me about this as well, is he's literally in sunshine and dead stop traffic. But you look ahead and you see the wall of cloud and you know that's where the lake effect's going. And it's snowing so hard there that the cars are backed up out of the band into the sunshine. It's really crazy. Some of the most difficult things you could ever forecast, all right? It's absolutely crazy. All right, so incredible snow totals, 6 inches in 30 minutes, 12 inches in an hour. I mean, think about that. A foot of snow in an hour. I mean, that's just crazy, all right? So you get the point. Incredible snowfall rates, incredible snowfall totals, and the highest totals you're going to see east of the Rockies, especially in that Oswego area, east of Lake Ontario. All right, so here's some pictures Doug gave me over the years. This is looking from the National Weather Service in Buffalo, and look at that. I mean, what does that kind of look like in the distance? I mean, obviously the cloud tops are not like a supercell where you're going to get 50, 60,000 feet, but still, I've seen lake effect vents pushing 30,000 feet, which is very significant with snow. Anything over 10,000 feet is pretty good. 20,000 feet is really good, but it looks very convective, right? That's because it is. It is convective. You can see that in the distance there. That's nowhere near as strong as some as you will see. This is an event we're about to talk about. They used to name these events. This was called Lake Effect Storm Gary. We'll talk about this, which at the time set the record for Buffalo. I'm not 100% sure if it's been broken since then, but one of the heaviest snowfalls in Buffalo history. And we'll move into that. They used to name these storms. I'm not exactly sure why they stopped. I'm sure there was some confusion, even though now they name winter storms, at least the Weather Channel does. It seems to cause a lot more confusion to me. I just, hey, the 93 storm, the 96 storm, but they did used to name these storms. So this one we're going to talk about was an interesting event, all right? Some of the storm statistics. Storm total accumulation, 38 inches in Buffalo, all right? And this was the most snow in a 24-hour period. I think that's still the record for downtown Buffalo or for the airport. I still think that is. It could be wrong, but regardless, one of the strongest storms in Buffalo recorded history at least. Broke previous 24-hour record of 25.3 inches, 2 feet of snow in 8 hours. I mean, that's just crazy. Even though that sounds so crazy to me, living where I do and even seeing the nor'easters I've seen, but for lake effect belts, that's actually somewhat normal. It's kind of crazy to think about that. Snowfall rates of 2 to 5 inches per hour. Again, you can get them higher. So, pretty amazing storm. So, it also produced nearly half the average snowfall for Buffalo. I mean, Buffalo gets a lot of snow, but it's nowhere near as like the belts to the east of Ontario and also the areas south of Buffalo. So, what was interesting about this event is it wasn't like, some crazy synoptic scale type thing went through. But what was interesting was the air was incredibly cold for this time of year, all right? And this is where the mistakes started happening, okay? So look at that negative tilt trough. It's not like it's the strongest system ever, but it brought in some really cold air, especially for that time in December, way colder than they normally see. And this is where they started making some mistakes, all right? So the forecast was completely blown. And when I say completely blown, I'm not going to say they didn't call for snow. They did call for snow, but nowhere near what they actually got. And we're going to kind of break that down and talk about it. So you can see, low level moisture here. You definitely in Buffalo would want to check down there, but it was good to go. Good wind that is, all in the same direction there. So that's always important. You want it, again, you don't want shear. And you can see that actually the moisture continued to go up. So this was a really good event, all right? You starting getting the equilibrium level pushing, 700 millibars, 10,000 plus feet, that starts becoming significant, all right? So a couple things that happened here where they made a mistake, all right? So let's first talk about the ingredients. There's a 25-degree difference between the lake and the 850 millibar level, all right? So that was significant. You had minus 18 degree temps at 850, and you still had relatively warm water since it was earlier in the season. And this was a great setup for what? A lot of rising motion, all right? 25 degrees difference, that's significant. What would that lake index be? Minus 12, all right? So that's pretty significant there, all right? There was light shear and the winds aligned southwest. But keep in mind, there's a big difference between 230, 240, 250, right? If you're in that 245 range, that's getting close to the sweet spot for Buffalo. Now, remember, there's obviously a range between the northern suburbs and the southern suburbs. And if you lived in a place like Buffalo, you'd want to look at that in a little bit more detail. But 245 is pretty good for Buffalo. You start going 250, 260, where's that band? It'll be south of Buffalo. If you're more 230, that band will be north of Buffalo, all right? So just the slightest shift in wind can make all the difference in the world, all right? There was a ton of Arctic air loss, so that wasn't a problem. Lake-induced equilibrium level is near 18,000 feet. abundant low-level moisture, so everything was pretty much in place. And you have negatively trough access to the Great Lakes with several shortwaves that, you had moderate DPVA, but that just enhanced it, all right? Now, you get this without the shortwaves, but the shortwaves just enhance it and make it even better, okay? So what happened? All right, so especially back then, and everyone's getting better, and obviously, with time, it's almost 25 years ago now. People are going to get better, things are going to advance. But they used to do this thing where early on in the season, they would use 850 as their steering wind, or as where these bands would set up. And then later in the season, when it got colder, they would use more 925, all right? So they made a mistake of doing an overgeneralization, all right? And this happens a lot in weather. You see this a lot with parameters with severe weather. Cape's only 1,500. It's not going to be that bad. Well, the normalized Cape is really high, so it depends on where the Cape is. So one thing I talked about before, snowflakes do not have a GPS or a calendar. It doesn't know it's December 10th. It doesn't know it's February 10th. Doesn't care. It doesn't matter, all right? If it's really, 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 really cold, it doesn't matter if it's December 10th or if it's February 10th, or the opposite. It could be really warm in February 10th. Weather's only going to react to what's actually happening, all right? So you start using these thresholds, you start getting yourself in a lot of trouble. So they made a mistake of going, early in the season, we're going to use a higher level because typically it's warmer events, right? Yeah, the air aloft is cold, but it's not usually as cold as it was in this event. So they usually use the higher 850 steering flow. And then later in the season, they normally would use 925, but because it was early on, they didn't use the 925 steering flow. They used the 850. I'm going to show you that there's even a better way than this, but keeping this simple, they should have used more than 925, even though it was early in the season, because it was so cold aloft. It was more like what a later season event would be. So they had everything right. They had it all right. They had the ingredients right. They had, all the different parameters together. They had their forecast correct. But the one thing they made a mistake on is they used the steering flow at 850 instead of 925. What you really want to do is you want to look at minus 12. Why minus 12? Well, where's your snow growth region? Minus 12 to minus 18 is your prime region. So in reality, you want to find in my opinion, and there's always a little subjective nature to all this, but you really want to find that minus 12 line and look at the winds at right around there, okay? But at the very least, understand that you can't use this early versus late season, all right? Just because it's December 10th doesn't mean you use 850 as your steering flow, and that's what they did. All right, they thought, early season, we're using 850, when they really should have used 925. And because of that, that was the difference between Buffalo getting some snow and their largest snowfall in 24 hours in history. All right, so this band started to move, and it does move through Buffalo. And, they did get, 6, 12, they probably got close to a foot of snow. It's not like they didn't get snow, and it's not like snow was expected or it wasn't expected. It's just there's a big difference between 6 to 12 inches of snow and 38 inches of snow, all right? So Doug told me, because he was around there during this time, he was interning at the Weather Service in Buffalo, that at this point, the band set south, and people, literally the local meteorologists there, were on air and saying, hey, the band has moved south, we're done with our snow, you can go out and enjoy the rest of your evening, because I know 6 to 12 sounds a lot to us, but to them, it's not that big of a deal in general. People thought, okay, it's over. Well, by morning when people woke up, the band was right back over Buffalo. And again, they should have used 925. Even though it was early in the season, it was like a later season event. Now, minus 12 is better, but at the very least, understand that, all right? So the band set up, and they got crushed. And, luckily in Buffalo, you usually have more times to redeem yourself. It's not like the South. You blow a snow event and you don't get another shot for maybe a year or two. You do get plenty of shots. But even in Buffalo, if you're calling for, you get 6 to 12 inches and you tell everyone it's over with and they wake up and they got another 2 feet, you're going to hear about that, all right? And what's crazy is they had everything right. They just made an assumption that was wrong, okay? And that's why you got to be careful. I give you tips. I give you these tricks, all right? But these tricks and tips are going to change with time. If I give you a bias now, 10 years from now, it might be a different bias, right? And be very careful about using parameters, being very careful about, early season we use this, late season we use this. Again, Snowflake doesn't have GPS or calendar. It doesn't care. If it's minus 18, it doesn't matter to the snowflake that it's December 10th. It's minus 18 aloft, okay? So that's something very important. All right, so snow totals were pretty crazy with this event. A great gradient on this. There was some road there where the gradient was almost 3 feet in like 4 or 5 miles. So, pretty awesome storm. And the forecast was blown simply because they used a trick with early season steering that didn't work out because it was really cold for this time of year and it wasn't like an early season event. And then they had a second event off of Ontario. Things started to dry out there, and then the wind shift, and you had a secondary event off Ontario. All right, and so here some of the satellite imagery from this event. So some key questions you got to ask yourself is, will there be a lake effect? And if so, where? And that's where the steering winds are really important. They used to use this early versus late season, but I've talked enough about that why you don't want to do that. I like looking at minus 12. That's just what I've used. That's what Doug has shown me over the years. It works really well. Nothing's perfect. But I just keep it simple. Where is my minus 12? I'll go on Buffett. I find minus 12. I look over. I look at the steering flow. And, that's where I'm going to have the steering flow set up. Now, sometimes it's easy. Sometimes there's almost no shear, and it's kind of hard to mess it up. Then other times there's 20 to 30 degrees of shear. And while, yes, this isn't how you get the record-setting events, that's where it becomes more difficult because if there's more shear, it's hard to pinpoint that steering wind, right? So parallel versus perpendicular lake makes a big difference as well. I'll show you some of the examples of that. If it's parallel, you have a longer fetch and you have more dense, stronger, more confined band. If it's more parallel, like Lake Erie, yeah, you have enough fetch, but they're going to be more fibrous. They're going to be not as strong, and they're going to be more kind of like broken apart. They're going to look like little pieces instead of one singular piece, all right? And then I talked about this, watch for multiple lake interaction. That's just going to enhance the moisture profile and just make the bands even stronger. All right, so that's more of a singular event or a singular band. Nice parallel flow, and you're getting that nice strong band. In this area, you might be getting 2, 3, 4 inches of snow per hour, and just to the south, nothing, all right? So that's a pretty good band set up there. This is more fibrous. This is more that perpendicular flow. You see how it's more fibrous, and a lot of times the only way to really see this that well is on clear air mode on the radar to really see it. Yes, it's snowing, but that is much different than this. This is really hammering somewhere where this, yes, it's snow, but it's nowhere near as strong, all right? Again, this is the hose that's going. This is I'm putting my finger over the hose, all right? What's going on here? Well, perpendicular, but you have a little bit of a dual lake interaction here, and that's why this band is a little bit stronger where these aren't, all right? It's not like these are overly strong anyway, but this one's stronger because you're starting to connect with another lake, all right? Kind of cool to see that. A few other things here. I talked about this already. The accuracy of the model QPF, it's worthless, all right? Even mesoscale models are unable to resolve such a tremendous gradient. I mean, we're talking microscale stuff that's going on here that you're going to have incredible gradients of snow. And the case study I'll show you again is like 5 feet in, 5 miles. Absolutely insane, all right? So again, QPF is worthless. Don't even use it. You're going to assess the ingredients, and then when you assess the ingredients, you want to know the duration. So this ingredients equals this amount of snow per hour, and I think it's going to last 12 hours or 24 hours or 36 hours. Obviously, the longer it lasts, typically, especially if the ingredients stay in place, the heavier the snow, the bigger the events. All right, that's how you get the 100-plus inch events. It's not like you get 100-plus inches of snow in one day. You get it over days, all right, several days. Forecast sounding sites may not be representative of the rest of the area. That's another thing you got to be careful about. You might pull up a forecast sounding site for Buffalo, and maybe Buffalo, the conditions aren't perfect, but just to the south of it or just to the north of it, the conditions might be much better. All right, so you got to be careful with that. But in general, what you're doing is looking at those forecast sounding, you're assessing the ingredients, you come up with an area. Or you use ingredients to come up with a snowfall rate and then use the duration to forecast that, all right? So the ingredients and duration versus the model QPF, don't use the model QPF. And be careful with the wind, right? Like I told you, 245 is about the sweet spot for Buffalo, but Buffalo is a big city, right? I mean, it's not like New York City, but it's like 1 million people or so. So the northern suburbs versus the southern suburbs would be different, right? So If it was more 250, 260, you start getting into the southern suburbs. If it's more 240, 235, you're going more in the northern suburbs. So experience will help you there. Lack of moisture in the snow growth region, this usually isn't a problem. Usually you have so much rising motion. Um, you know, Obviously in the gradients are just borderline, maybe not so much. But in general, your lake-induced equilibrium level is well into the snow growth region, and this is usually not an issue with lake effect events because of the instability present. Fluffy versus wet snow, this is where snow ratios come in. Yes, some of the highest ratios you'll see are usually in lake effect events with all the omega, but you can still get wet snow. All right, so you got to analyze that. Impact of wind speed, that also is important. I told you the more fluffy the snow, the more effect wind will have on it, right? So that will affect snow ratios, especially when you get in that 30 to 50 range, because that's the tricky stuff there. And then also, what else is it going to affect, all right? Remember, if you had less of a fetch, if you had slower winds, you might be able to get away with that, all right? Also, if it's a blizzard, you might want to talk about that. The winds are 35 miles per hour or higher. It's something you want to talk about. And also keep in mind, you do also get lake effect rain. It's not just snow. All right, so what would you forecast? We'll keep this quick because we're going to do a little case study, and I'm going to give you the file so you can go through it yourself. All right, so on this one, a couple things. The winds look like there's a little bit of shear going on here, but really the low levels, there is some moisture, but it's lacking, right? It looks to me like there's not enough moisture. Obviously an older sounding, so the details are probably not as good there. Same thing with this one. Details are not perfect, but look at how much more aligned the winds are, more saturated, higher up. So this is a higher equilibrium level, more saturation, more uniform winds, less shear, and actually this led to a decent event. Nothing compared to some of the events you can get there, but you can see these bands of snow that set up off Ontario, off Lake Erie, and nice band there off of Erie, moving through Buffalo, and they got, not. It's crazy to say that 18 inches is not that big a deal for lake effect, but really in the grand scheme of things, they can get way, way more than that. 18 inches in Washington, D.C., historic storm. 18 inches in a lot of these areas in the Great Lakes, not the end of the world. All right, but still, you see the setup on that. This one, pretty good moisture, good uniform winds. I would definitely expect good lake effect with that. Now, obviously, I would want to pull this in Buffkin and really look at it, all right? That's important. But then with time, what happens? It dries out. So if your moisture profile dries out, then, again, the assumption always was the lake provides enough moisture. That's not always the case, all right? So you really need to look at that area there. And Buffkit will give you way more detail than this, obviously. All right, so a couple additional images here. This was a pretty famous event in Buffalo, and the reason why it was so famous was the time of year. This was more of a heavy, wet snow, and because the leaves, it was early in October that a lot of the leaves on the trees were still present, because of that, the snow accumulated in the trees and caused a lot of trees to come down. You get 2 to 3 feet of heavy, wet snow, and you got all the leaves, and the snow is accumulating efficiently on, the trees. You sometimes get trees to come down, and what happens when that happens? You get power outages, right? So that's what made this event really famous. Was it was an earlier season event, and it caused a lot of trees to come down and power outages, all right? So time of year, while it doesn't matter as far as whatever what the ingredients show you is what the ingredients show you, but understanding, hey, okay, it's early October. There's still leaves on the tree. Those are things you do want to think about, okay? That is something important to think about. Nice band from that event. Look at that. Just coming through there. Pretty continuous event. This was just a random event, but what was cool to me was, less fetch, more connection here, more of a, stronger band versus here, not quite as much of a connection. Kind of interesting to see that. This is obviously closer to this. There's more of a landmass in the way here, so this connection causes a stronger band. Pretty interesting. This one, obviously, what's probably going on here? More wind shear. Yes, you're probably right at that 30-degree threshold, so you can still get lake effect snow, but you see how it's more spread out, the finger over the hose, right? All right, here's a synoptic scale event where, the coastal low moves off the East Coast, and what happens? It clears up stormy, right? The synoptic scale event moves out, the cold air comes in aloft or the relatively warm lakes, and then you start getting lake effect streamers, right? Assuming that all other ingredients are in place. And then you see how some of these streamers can move all the way to the East Coast. It's kind of like that weird one I showed you in Huntsville from Lake Michigan. All right, I remember in DC I saw it a few times. I think even can't remember the year, but it was on Christmas Day Christmas night that we had a band come in once. So they can move far inland, but obviously if it moves inland, you're not talking about ridiculous amounts of snow. It's going to be 20 to 30 miles from the lake where the best snow is going to be. All right, so quickly, I'm going to go through a case study from Buffalo, November, I think it was 19th through 21st, 2014. This was crazy, all right? Buffalo itself got away with not having too much snow. They got lucky, but suburbs just to their south and to their east, because the band set up to their south and to their east, had up to 65 inches of snow, all right? So very historic event. 65 inches of snow in, a couple days, that is pretty significant. I'm going to put the bucket file in the class. I also added some images. I'm also going to put the summary from the National Weather Service on this event, so that way you can go through it on your own as well and look at these things in more detail. I pulled a few images to talk about, but you'll have the file, you'll have the summary, so you can really go through this in more detail yourself. And of course, if you have questions, you can ask me anytime. All right, so this is the beginning of the event. It probably has already started for a couple hours here. This is 0Z. This would be Sunday night. And at first, the band did move a little bit, all right? The winds were kind of shifting around a little bit, so it kind of formed just over Buffalo to the south. It shot up to the north, and then it went back down to the south. And once it's set up, after about 3 or 4 hours of kind of pivoting a little bit, it's set up and just sat there for a couple days, all right? But let's look at a few things. First thing, you see down here this lake temp? Well, that's cool. It's going to tell you what, you'll be able to put the lake temperature in. That's essential. If you don't know the lake temperature, how are you going to know the difference between the lake and 850? And the good thing is there's a huge buoy network through the Great Lakes, and the Weather Service are following this, so you'll have the information provided that you'll know what the lake temperature is. In this event, the lake temperature was 9 degrees Celsius, all right? So it was still fair. I mean, look, November, right? So if you went back in the day, you're like, oh, we're using 850 because this early season event. Nope. Look where minus 12 is, all right? And we're going to look at that here in detail. So you put the lake temp in there, and then it'll give you the difference, and it has these different thresholds here. Look, Buff Kit obviously was made for this. You could look into those thresholds, but I still think it's better for you as a forecaster to know your area and to know the thresholds for you, because it may be a little different in Buffalo versus, I don't know, somewhere like Oswego, all right? So make sure you look at that. It gives you equilibrium level. You got your CAPE, you got your normalized CAPE. It's got all sorts of cool stuff. I clicked on lake index. So at this point, your lake index is -4. So what does that mean? Well, let's look at the difference here. We have a 17-degree difference, all right? So if your 850 is -8 and your lake temp is 9, that's a 17-degree difference. And we know 13 gives you a lake index of 0, so 17 gives you a lake index of -4. And look at that. It gives it to you right there. It's really cool, right? So at this point, you look at right around -12. Again, I'm not using 850 or 925. Now, if you force me to it, because it's so cold aloft when this event really gets going, I guess 925 would be better than 850. I mean, for sure. But still, I think it's best. Look at that -12, all right? That's going to give you a good idea, all right? So at first, this band is right over Buffalo, maybe a little bit south. It quickly pivots north, and then it starts to move south of Buffalo and just sits there and sits there and sits there, all right? So let's look at it, right? Let's look at how this changes and how these things change with time, all right? I'm just going in 5-hour increments, all right? So 5 hours later, now what's happened? Wow, that lake index came up quick. We're already at -11, all right? We have now a 24-degree difference. That's significant. Your equilibrium level is hitting about 10,000 feet. Your normalized CAPE has come up a lot, all right? Yeah, the CAPE is not extreme, but still, it's in the right place. You're getting more fat CAPE, which means what? Faster updraft acceleration, which means what? More convection, stronger, precipitation amounts. It really ties into this well, okay? And the lake temp hasn't changed. All right, lake temp, the whole event is about 9 degrees Celsius. Okay, so this is definitely doing what? Everything is strengthening. But now what's happening? That band now is set up south of Buffalo. All right, so let's go to the next. Let's go to hour 10. Now we're at -13. So what's happening? It's just getting more and more unstable. Your normalized CAPE is going up. Your overall CAPE is going up. Your equilibrium level is going up. Now you have a 26-degree difference. You have double what you need to get lake effect snow, all right? that is pretty darn significant, all right? Your tops of the cloud are well over 10,000 feet. Now let's look at minus 12. All right, the minus 12 is right around now 259, 260. And what you'll see in this event, once it locks on around like 258, 259, 260, it just sits there. And as these ingredients are maxing out, like if I looked at something like this, and especially as I go on, let's go another, 5 hours out, minus 13, 15,000 feet equilibrium level, 26-degree difference, good normalized cape over 1,000. Here's my minus 12. Look at that. It's sitting right at that 258, 259. So it's right in that sweet spot that would be just south of the city of Buffalo. And I'll show you some cool imagery of that later. If I was looking at this would be getting close to what I would agree, extreme. I guess that's a word you could use for it. I would probably be going like 3-4 inches per hour at this point. So I would count how many hours at this more extreme level, and I would just start adding the accumulation stuff. And what's crazy is I remember this event, and I remember thinking to myself, oh, they'll get at least 48 inches of snow. And you got to have some guts to go, hey, 48 inches of snow. And I was too low. They had actually 5 feet of snow, right? So it's just crazy to think of that. But the good news with this, at this point, there's not a lot of shear, right? So even if you did use more 925 versus 850, you're lucky in this sense because you're not going to blow it as much. But if there was a 10-degree or 15-degree difference, that's where minus 12 versus picking 850 versus 925 makes a big deal, right? So if you're using early season 850, yeah, it's not like it's a huge difference. You're only talking a couple degrees at this point, but still, you wouldn't want to use that, all right? I always find the minus 12, and especially if there's spread, that's where that's going to come more into play. We'll go to hour 20. It's still really high. Equilibrium's gone up even more. Normalized cape's really high. Good fat cape, good updraft acceleration. And what's crazy is you see this? See that here? It's showing 0 precipitation, right? Now, we're pulling up a file from Buffalo, right, in the airport there. And really, at that point, you're right. It probably isn't 0 precipitation. But just to the south, it's through they're getting absolutely pummeled, right? Again, QPF is worthless. It's just so tight of a gradient. I don't even bother with it. Again, let's add up the ingredients, let's add up the time, and that's how I go with my snowfall amounts, all right? And then I went to hour 23 because the normalized cape was the highest there, highest equilibrium level. The lake index is still minus 12. This is nearing the peak. And what eventually happened was it just sat there for a couple days, and I'll put the summary so you can read all about it. And eventually then the band started to quickly move off to the north and just dissipated, all right? So by Wednesday, I think the event started Sunday night, and by Wednesday morning, it really started to dissipate. But the damage was done by that point. 65 inches of snow, pretty crazy, all right? So hopefully that was helpful. Again, I'm going to put the file in there. You can look at all this stuff. There's tutorials. Again, training is going to help you if you want to give in more detail. But at least you got a cool event that you can look at. You can look at these hours. You can look at these parameters and everything here. And this is what Buffgate was made for, all right? So it's really cool. I'll end with this. Look at that. This is Buffalo looking south. What does that look like? A wall of snow or whatever you want to call a wall of cloud, snow. And this is what I was talking about. Like literally there'd be cars that can't go anywhere. And then as you move out of it, you're maybe not sunny in this circumstance, but still clear. It's no precipitation's coming down and you're in dead stop traffic, right? That's really amazing. Now, this is more of an extreme event, but look at that. You could see the gradient. You could literally see how tight that gradient is, right? Looking south, and then here's another picture where you can really see it. Look how convective this is, right? This is like thunderstorms with snow. That's basically what it is, right? So convective snow, and look how tight that gradient is, all right? So again, QPF's not going to do so well, and a model is pretty much worthless. Use ingredients, add up the time, and again, it's going to take practice, all right? Now, this is more extreme. You're not going to see this every day. That's amazing. Beautiful in many ways. For me personally, I would love to get into something like this and just get a hotel and sit there for a week and enjoy it, all right? But that's just me. But still, if you're in those areas, it's going to take time. Get a notebook, get a journal, practice a lot with this. Look at your ingredients and what it led to as far as snowfall rates, And with time, you're going to be able to fine tune it. You're never going to be perfect because it's one of the hardest things to forecast, but you can get a lot better with it. Okay. So hopefully that was everyone enjoyed that. I mean, I love lake effect snow. It's one of the cooler things I think in weather. And we will move on now into lecture 12. So I'll be back with that shortly.